Hello and good morning friends, welcome to CEC-UGC live lecture. Dear friends, with another lecture on operations research. Today we are going to talk about dynamic programming, and for this we have again with us in our studios Dr. Subhash Kakkar. Dr. Subhash Kakkar, as you know, is an eminent professional. He is an eminent academician, as well as, I would like to tell you all, he has a vast practical, I would say, corporate experience. He conducts various workshops, seminars at both national and the state level, as well as he carry out various management development programs, as well as faculty development programs, as well as I would like to tell you all that he is master in SPSS, that is Statistical Package for Social Sciences. So taking advantage from his experiences, let's conduct today's lecture and understand what basically dynamic programming is. So first of all, I would like to welcome our guest, Dr. Subhash Kakkar. Dr. Kakkar, welcome to the EduSet lecture, and I hope that the way you used to deliver your lectures with the help of eminent or I would say excellent examples, this lecture is also going to be one of the finest lectures of yours. So over to you, sir.
Thank you, Gitika, for such a wonderful and elaborate introduction. I welcome viewers to today's topic and today's lecture, which is basically a part of our series on operations research. And today's topic is dynamic programming. There are so many topics which are to be covered in operations research, like transportation model, assignment problem, traveling salesperson problem, game theory, Markov chains, PERT and CPM. And today we are going to learn, of course there are other programming techniques also, linear programming, quadratic programming, and integer programming, goal programming, and today we are going to study dynamic programming, which is a distinct content based topic, and this has a specific application in our day-to-day life, whether we talk of organizations, whether we talk of any operations management in maybe hospitals and in supply chain management, and this particular topic is very useful. This has its use in almost all the functional areas. So today we are going to spend some time on this particular subject. Dynamic programming says that our solution is based on the segments of the problem. The main big problem is divided into segments in the sense that problem is divided into parts, and each part gets a solution based on some algorithm, and then solutions of these segments are combined together to get the net result as a solution to the main problem. So we are going to study how to carry out this dynamic programming to solve our problems in an effective manner. The term dynamic programming was originally used in the 1940s, and this term was used basically by Richard Bellman to describe the process of solving problems where one needs to find the best decisions one after another. What is the meaning of one after another? Because the problem, as I said earlier, is divided into different segments. It is broken down into different parts. The main problem is divided into different parts, and each part is then worked out for its solution. And there are so many then solutions in the form of different parts, and these are then finally combined to get a solution to the main big problem. In 1953, because working on this dynamic programming started during 1940s, after the decade in 1953, Professor Richard Bellman refined this to the modern meaning, referring specifically to nesting smaller decision problems inside the larger decision, which is a big problem. Smaller decision based on the big decisions, and the big decision is formed by adding up all the smaller decisions, and these smaller decisions are to the segments of different problem areas. Bellman's contribution is remembered in the name of the Bellman equation. Bellman has given us an equation and a central result of dynamic programming, which restates an optimization problem in recursive form. The recursive form means when the problem is divided into different parts, at each part, which is part of the one state, we have the best solution for this particular part, and the solution of these parts are then combined together to get a final solution to our problem. So, dynamic programming is a method for solving a complex problem by breaking it down into a collection of simpler sub-problems. This is the main definition of dynamic programming. I will repeat it. Dynamic programming, and the short form is DP. DP is a method for solving a complex problem by breaking it down into collection of simpler sub-problems. I will give you an overview of dynamic programming. Dynamic programming is both a mathematical optimization method and a computer programming method. So, it is a combination of two things. One is a mathematical optimization technique based on mathematical theory, mathematical principles. So, we use mathematical principles to dynamic programming, and these mathematical principles are used to the different parts of the problem, and we get the solutions to these small problems. And the second part is, this is also based on computer programming methods. In computer programming also, when a coder wants to find a solution to the problem, he writes algorithms in the form of solutions to the problem in a segmented form. And finally, he combines all the solutions in the computer programming and gets a solution to his main problem. So, it is in two parts. One is mathematical optimization. We optimize the results and combine together. And in the second form, we make use of the computers in the form of computer programming to get solution to our problems. Problem is divided into different parts, and each part finds its solution through computer programming techniques, and finally these are added together to get a final solution to the problem. So, in both contexts, it refers to simplifying a complicated problem by breaking it down into simpler sub-problems in a recursive manner. Recursive manner means we follow the same procedure to the different parts of the problem. We find a solution, we come back and put the solution in order, and then we go to the second part, then third part, and the fourth part, and the last part, and in recursive manner, and then finally we get a solution to the problem. Basically, in this slide we have studied that dynamic programming is both a mathematical optimization technique as well as computer programming model. Both are used to find a solution to our main problem. Problem is broken down into different parts, and each part is then worked out for its solution, and small solutions are added together to get a solution to the main problem. While some decision problems cannot be taken apart this way, decisions that span several points in time do often break apart recursively. The meaning is, while carrying out the solution to the segmented problem in a recursive manner, we finally get a solution to our main problem. Bellman, who gave the idea of dynamic programming, called this the principle of optimality. The working of problem in a recursive manner, Bellman called it the principle of optimality because the optimization is being carried out using mathematical principles and computer programming techniques. Likewise, in computer science, a problem that can be solved optimally by breaking it into sub-problems and then recursively finding the optimal solution, the sub-problem is said to have optimal substructure. The main problem is divided into sub-problems and optimization is carried out. We find a solution and this optimality is spread over the problem and we get a solution to the main problem. This is the basis of working with dynamic programming to get a solution to the problem. If sub-problems can be nested recursively inside larger problems so that dynamic programming methods are applicable, then there is a relation between the value of the larger problem and the values of the problems. In the optimization literature, this relationship is called Bellman equation. Richard Bellman has given us an equation and this equation is known as Bellman equation. He says that through this equation that if a problem can be broken down into parts and value of the solution of each part has a bearing on the final solution of the main problem. In other words, the solution of the main problem is dependent on the solution of the segment of the problem which we have already carried out. So, these solutions are interdependent and this is given by Bellman equation. Dynamic programming. In mathematical optimization, in terms of mathematical optimization, dynamic programming usually refers to simplifying a decision by breaking it down into sequence of decision steps over time. Since it is not a stationary decision, we keep changing our decision over time. Today, we have taken a decision for a particular segment of the problem, then we take a decision on the other segment of the problem and we combine the results. So, we change our decision to the final result and that is why we call it is a dynamic in nature, it is not stationary. Our decisions are dynamic in nature. We carry out the decisions on the segment of the problem in a recursive manner and finally we get a solution to the main problem over time. So, this is done by defining a sequence of value functions. So, now I am going to tell you the nutshell of dynamic programming. And value functions are, for example, V1, V2 till Vn with an augment y representing the state of the system at times I from 1 to n. So, V1, V2, Vn are the value functions with an argument y representing the state of the system at times I from 1 to n. So, state I is defined. I can have different values depending upon the number of states, and each time we have a solution, and solution is in the form of a value, say, which we have already stated V1 to Vn, and similarly, and the states are called 1 to n. So, 1, 2, 3 and V1, V2, V3 and Vn, and these are values, and 1, 2, 3 are states. The definition of Vny is the value obtained in state y at the last time n. So, we have to understand carefully what is the meaning of Vny. Vn is the value at time n and at the state y. The values Vi at earlier times I is equal to n minus 1, because we are talking about the time Vn. Earlier to Vn is n minus 1, and earlier to n minus 1 is n minus 2, and so on. At the end we will go up to 2 and 1 state. So, if we go back from the state Vn, I will have the values n minus 1, n minus 2 till 2 and 1. And then these are found by working backwards. Since we are working backwards, so we will be finding the values in backward condition using a recursive relationship called the Bellman equation. For example, y for I is equal to 2 and till n, Vi minus 1, V is the value at I minus 1, okay, one step previous to Vi. At any state y is calculated from Vi by maximizing a simple function, usually the sum of the gain from decision at time I minus 1 and the function Vi at the new state of the system if this decision is made. So, this says that if we are taking a decision and we have V which is Vi minus 1, which is one step prior to Vi, at any state is given by y, and is calculated from Vi by maximizing a simple function, usually we take the sum of the gain from decision at time I minus 1, because now we are getting the value at Vi minus 1, and then we will consider the state also I minus 1 and the function Vi at the new state of the system if this decision is made. So, in this nutshell, we have divided the problem into different parts, and each part has a state, and the states are numbered I from 1 to n, and similar the values are also numbered from Vi to Vn, and we talked about values are a step prior to Vi, which is Vi minus 1, and the state is also called I minus 1. Now, since Vi has already been calculated, so we have already calculated Vi, and we were talking about a step backward. Now, since Vi has already been calculated for the needed states, the above operation yields V value I minus 1. So, at a state I minus 1, we were talking about Vi, and we are going a step backward for those states. Finally, V1 at the initial state, V1 is the initial state. So, V1 at the initial state of the system is the value of the optimal solution, and this optimal solution which we are looking for. The optimal values of the decision variables can be recovered one by tracking back the calculations already performed. So, we have performed the calculations prior to starting the calculations on the main problem, and we have discussed Vi and Vi minus 1 also. So, this gives us the optimal values of the decision variables, and which can be recovered one by tracking back the calculations already performed. Now we have 4 steps for solving problems with the dynamic programming method. Now, we will be discussing these 4 steps, which are carried out for finding a solution to the problem. The first and the foremost step is divide the original problem into sub-problems called stages. We will divide the main problem in different segments, and these segments are called stages. The second step, solve the last stage of the problem for all possible conditions or states. The point to be noted is, we will start our solution from the end, and the end we must know what we want to achieve. There are so many segments of the problem, they are connected in sequence. The last part in this sequence or last part in the chain, we will work for the first time, and all other solutions will follow. We will give priority to the end of the solution what we want. We will start from the end and we will go to the start, and we will take a step at the start point depending upon the end we want. So, moving backward from the last stage, so we have to start from the last stage, which we have already explained in the second step. Solve each intermediate stage successively. This is done by determining optimal policies and solutions from the stage to the end of the problem. We are starting from the last stage and we have to go to the first stage, and each stage we have to take optimal decision to get a optimal solution till we reach the first stage. Starting from the end stage, we have to reach at the first stage, and this is a third step which had to be followed to get a solution to the problem. Now, the last step, the fourth step in the process of solving a problem is obtain the optimal solution to the original problem by solving all stages sequentially. First, we have made the sequence, we have made the chain of stages, we have identified the last stage, we are working on the solution on the last stage, and we are moving backward. Each stage we have to find its best possible optimal solution, and the final step is solution to the main problem, solution to the big problem is based on the solutions of these all stages, and these are combined together to get the net solution to the main problem. And these 4 steps are always to be completed for getting a solution to our problem using dynamic programming technique. Now, we will discuss what is the difference between dynamic programming and linear programming. Means other programming techniques are being compared with this particular technique, which is called dynamic programming. The dynamic programming is different from linear programming on 2 counts basically. On 2 basic points, these are differentiated. There does not exist a standard mathematical formulation of dynamic programming. This is a fact that dynamic programming does not have any fixed mathematical principle or theory based on which we get the solutions. Each time, each problem, each segment, we have a different method to get its solution. So, every time we have a different algorithm to get a solution to the segment of the problem, but it is not so in linear programming. In linear programming, we have a definite algorithm, we have a definite procedure, we have a definite method to solve it, maybe in the form of simplex method and other methods. There is no algorithm like simplex method in dynamic programming, but in linear programming we do have such methods which are predefined before getting the solution to the problem. Dynamic programming is a technique which permits us to dissect difficult problems into sequence of sub-problems which are evaluated by stages. In dynamic programming, it is possible to dissect the main problem into different parts, and we use different mathematical theories and mathematical principles on each part and each stage of the problem to get solution to the problem. But this is not the case with linear programming. Linear programming has its own method by which we get a solution to the problem, and dynamic problem, we dissect the problem into different segments, different parts, and get solution to the problem. Linear programming is a method which gives single stage, that is one time solutions. Linear programming is a stationary model. It gives us a solution once only. But in case of dynamic programming, the concept is different. DP has the power to determine the optimal solution over, say, a 1 year time horizon. It is based on time horizon. It is not stationary, it is not fixed. When we talk about the dynamic programming solutions, these are based on time, maybe for 1 year, and for 1 year the solutions are based upon 12 months solutions, each month solution, and finally these are added together to get the result for the full 1 year. Dynamic programming has the power to determine the optimal solution over, say, a 1 year time horizon by breaking into 12 smaller 1 month time horizon problems and to solve each of these optimally. Each month the problem is solved optimally, and each month's solution is added, and we get the final result for the 1 year horizon, 1 year decision. Deterministic dynamic programming. Dynamic programming, simply DP, determines the optimum solution to an n variable problem by decomposing it into n stages, with each stage constituting a single variable sub-problem. Problem is divided into n segments, n stages. And the recursive nature, what do we mean by recursive nature of computations in DP? Computations in DP are done recursively in the sense that the optimum solution of one sub-problem is used an input to the next sub-problem. This is the meaning of recursive computations. Problem is divided into segments. Solution of one stage is used as an input to the second stage. Output of second stage is used as an input to the third stage. This is called the recursive computational technique. By the time the last sub-problem is solved, the optimum solution for the entire problem is at hand. When we have solution to different stages, and then it means we have a solution to the main problem in our hand. The manner in which the recursive computations are carried out depends on how we decompose the original problem. What sort of method, what sort of mathematical principle we are going to use, and then we get the final solution. In particular, the sub-problems are normally linked by common constraints. As we move from one sub-problem to the next, the feasibility of these problems and these common constraints must be maintained. As a rule, as a policy, we have to maintain the constraint throughout the problem what we are solving. A small description about DP. Hence, dynamic programming is a technique that can be used to solve many optimization problems. This is a basic fact. DP can be used to solve a number of problems. In most applications, dynamic programming obtains solution by working backward from the end of the problem towards the beginning, thus breaking up a large unwieldy problem into a series of smaller, more tractable problems. And now we will give you an example also, because without example it is rather difficult to understand the meaning of dynamic programming. So far we have learned that dynamic programming, the problem is broken down into different stages and we find a solution to each stage to get final solution to the problem. And now I am going to give you an example of network problem so that viewers can understand the problem solving technique thoroughly. A network problem, many applications of dynamic programming reduced to finding the shortest or longest path that joins 2 points in a given network. There is a network and we want to find out maybe the shortest path and sometimes the longest path. Maybe we want a route from one place to another place and going through different points in the route so that we cover the shortest distance. For larger networks, dynamic programming is much more efficient for determining a shortest path than the explicit enumeration of all paths. Now look at the slide and different points are given and these are joined together with different routes and these routes are being added on the slide and the distances in kilometers are also written on each arrow and each arrow shows a path. Our aim is to come from A and we have to reach the point J, which is the final point. Say for example, A to B, the distance is 2 kilometers and from A to D, the distance is 3 kilometers. And similarly, all the distances are mentioned on all the routes. And all the routes which are possible are shown in this diagram. So we want to work out the smallest distance to be covered so that we reach the point J while starting from point A. So we shall be using dynamic programming technique. In this technique, we have to break it down into different stages and we have to start from the end stage. And that is a method to be followed as we have already discussed. We have to start from the end stage. Just see, we are going to start from the end stage only as we have discussed and we have to follow till we reach the starting point, rather beginning point. How we are going to do? We shall be using dynamic programming technique only. We shall be starting from the end point J and till we reach the beginning point A. Now this is the route plan which is given to us, and before solving the problem we must make this route program. Now starting from J we can reach H, because I said starting from the end point we have to go till A. The shortest possible route is HJ, which will have to cover 3 kilometers, and the arrow shows that it is coming from J point only. We are reaching H point coming from J point. Similarly, the next point is under I, which is 4 kilometers, which also gives us that we are coming from J. Rather, from I to J we are to reach. So from H to j is 3 kilometers, from I to j is 4 kilometers. So, that is why I have written j at the end of the arrow and j at the end of the arrow at the bottom also. Now, again we will go backward, we will reach E, F and G. We will see how many kilometers are to be covered and which are shortest in calculation. Next, E we have reached. So, E we have reached because E is connected to H, and the shortest possible distance to be covered is 1 kilometer only. So, we will add 1, 2, 3 and it makes 4 kilometers. So, 4 kilometers so far we have covered and we have reached E, and similarly we will reach F also. For reaching F, so we have to see from where we are coming. So, from F we are coming from I, which is 3 kilometers only. At the bottom Fi the distance is 3 kilometers and till I it is 4 kilometers. 4 plus 3 is 7, that is why we have written 7. Now, consider, say if we have to come from H, the distance would have been 6 plus 3, 9 kilometers, but the shortest distance is 7 kilometers, that is why we have written 7, and this is another stage. First stage covered H and I, and the second stage is now covered by so far E and F. Now, we will see at G also how much is the distance. So, at G it is 6 kilometers and 6 kilometers we are writing H. So, we are coming from H point, because till H it is 3 kilometers and G to H is 3 kilometers, 3 plus 3 is again 6 kilometers, that is why we have written at the bottom 6 kilometers and the arrow shows H. H means from H to G only. Now, look at the condition, had we added from I to G, how much distance would have been? Till I it is 4 kilometers, from I to G it is 3 kilometers, 4 plus 3 7. So, 7 is more than 6, that is why we have taken 6, which is the shortest possible route. So, 2 stages we have covered so far. Now, the next stage will reach B, C and D also. Now, reaching B. So, B will reach from E point, because on the arrow, so we have written E, and E will get 4 plus 7, 11. 4 plus 7, 11. Of course, we can reach B from F also. That will give us 7 plus 4, 11. That is another route which can be followed till B, so that we get only 11 kilometers add up together. Now, at point C, the distance to be covered is 7, and from E, we have to come from E only. Till E, we have covered 4 kilometers and we are to add only 3 kilometers to it. 4 plus 3 makes 7. And next, at point D, it is 8 kilometers only and we have to come from E. So, from E till E we have 4 kilometers and the distance from D to E is 4 kilometers, 4 plus 4, 8 kilometers. That is why we have written 8 kilometers. Any other route, if we take, will give us more kilometers. What we do not want? We want the shortest possible route. And finally, A point. We have to come from C, because till C we have totaled the distance 7 kilometers, 7 plus 4 is 11. So, this is the way to use dynamic programming to get a solution to the problem. What is our solution to the problem? We have to cover only 11 kilometers if we want to go from A to J, and the route to be followed is also given. We go from A to C and C to E and E to H and H to J, and total distance covered is 11 kilometers. There are alternate routes also. There are 2 more routes available, okay, and which will add up to only 11 kilometers. This solution is obtained using dynamic programming method. Thus, the optimum route will be optimum route. One of the routes is ACEHJ and the second route is ADEHJ. These 2 routes add up to 11 kilometers and the third route is ADFIJ. All these 3 routes add up to 11 kilometers only. So, this way we are able to find out the solution to our network problem using dynamic programming technique. So, in nutshell, what we have done so far, getting a solution to this problem, we started from the endpoint and the main problem was divided into different stages, and each stage we took the best possible decision. What was the decision to be taken in this case? Shortest possible route. At each stage we have taken this decision, means we have chosen the best possible route which gives us the shortest possible kilometers to be covered. Then finally, we have already added all these solutions, we have added all these routes to get a final route to our main problem. So, this way I have demonstrated the dynamic programming method which is used to solve the problem, and the value for this route is only 11 kilometers. An example, one more example, a simple example I am going to give you. We show how working backward can make a seemingly difficult problem almost trivial to solve. Suppose there are 20 matches on a table. I begin by picking 1, 2 or 3 matches. Then my opponent must pick up 1, 2 or 3 matches. We continue in this fashion until the last match is picked up. The player who picks up the last match is the loser. How can I, the first player, be sure of winning the game? Winning the game means the first player should not be the last person to pick up the match. So, how to do it? In dynamic programming, the first step is start from the end. End is the match which is left should be picked up by the opponent. So, start from there means give the last match to the opponent and then start in a forward direction till you get to the first match and take a decision based on what is the solution to the first match. This is a way to use dynamic programming to get a solution to our problem. So, I will explain the procedure to be followed in this case. If I can ensure that it will be opponent's turn when one match remains, I will certainly win. So, this is the solution to the problem. So, working backward, one step, if I can ensure that it will be my opponent's turn when 5 matches remain, I will win. Similarly, if I can force my opponent to play when 5, 9, 13, 17, 21, 25 or 29 matches remain, I am sure to victory. Thus, I cannot lose if I pick one match on my first turn. So, if I take the opportunity to pick the first match, then the last match will be picked up by my opponent. So, this is a way how to win this game. So, this is again a small demonstration to use dynamic programming. Characteristics of dynamic programming and applications. Characteristics number 1, the problem can be divided into stages with a decision required at each stage. This is the first characteristic of a dynamic programming application. And the characteristic number 2, each stage has a number of states associated with it. all the stages are interconnected. Each stage has a number of states associated with it. By a state, we mean the information that is needed at any stage to make an optimal decision. Characteristic number 3, the decision chosen at any stage describes how the state at the current stage is transformed into the state at the next stage, because next stage input comes from the previous stage output. This we have covered characteristic number 3. Characteristic number 4, given the current state, the optimal decision for each of the remaining stages must not depend on previously reached states or previously chosen decisions. This idea is known as the principle of optimality, given by Bellman, Richard Bellman. Characteristic number 5, if the states for the problem have been classified. So, you have to note that if the states for the problem have been classified into on of t stages, there must be a recursion that related the cost or reward earned during the stages t. Reward is nothing but the solution to the problem. Then t plus 1 till we have capital T to the cost of reward earned from stages t plus 1, t plus 2 till we have t. So, an inventory problem using dynamic programming method, we can use dynamic programming solution to the inventory problem also. Dynamic programming can be used to solve an inventory problem with the following characteristics. Time is broken up into periods, the present period being period 1, the next period 2 and so on, the final period t. At the beginning of period 1, the demand during each period is known. When we are starting to get a solution to our problem, we know that demand at different stages of the time period are known to us. At the beginning of each period, the firm must determine how many units should be produced. Capacity during each period is limited. How much production to be carried out should be known. Point number 3, each period's demand must be met on time from inventory or current production. So, there is a demand, outside demand for say certain product, and that should be met either through inventory or through production. That must be the rule. During any period in which production takes place, a fixed cost of production as well as a variable cost per unit is to be incurred. That is a fact. If something is being produced, is being manufactured, we have to cover the variable cost because the fixed cost has already been incurred. The fourth point to be considered is the firm has limited storage capacity. We cannot have unlimited inventory. Based on the limited storage capacity, we must know how much the company or the factory can store. This is reflected by a limit on end of period inventory. A per unit holding cost is incurred on each period's ending inventory. Okay, that should also be known. Inventory carrying cost must be known. And finally, the firm's goal is to minimize the total cost of meeting on-time demands for periods say 1, 2, 3 till t. So, in this model, the firm's inventory position is reviewed at the end of each period, and this each period can be 1 month. If you are talking about the total period 1 year, this can be broken down into month-wise requirement, and then the production decision is made based on monthly requirements. Such a model is called periodic review model. This model is in contrast to the continuous review model, in which the firm knows its inventory position at all times and may place an order or begin production at any time. There are two different methods which are used. Okay, now we have another example, another problem which finds its solution in the dynamic programming process. This is resource allocation problems. Resources in the organizations are limited and these be allotted judicially so that cost is minimum and the results are maximum. Resource allocation problems in which limited resources must be allocated among several activities are often solved by dynamic programming. And these resources can be in the form of expert labor and a critical equipment which has limited quantity in number available and the use is enormous. Enormous in the sense a particular special equipment is to be used at different project sites. So, this is a limited resource and the funds are also limited available and there are so many activities to be carried out. What should be the basis for selection of activities which should be completed in a certain period? So, this decision is given by dynamic programming solution. To use linear programming to do resource allocation, three assumptions must be there, because linear programming technique is used on some assumptions. I am repeating those assumptions. The assumption number one, the amount of a resource assigned to an activity may be any non-negative number. Second assumption is the benefit obtained from each activity is proportional to the amount of the resource assigned to the activity. So, principle of unity is applicable in this assumption. And then assumption number three, the benefit obtained from more than one activity is the sum of the benefits obtained from the individual activities. Means individual activity solutions can be added together. And in the second assumption, we have studied that results are proportional to the amount of resource added. Now, even if assumptions 1 and 2 do not hold, dynamic programming can be used. So, the problems where the assumption number 1, assumption number 2 are not applicable, we can make use of dynamic programming method. And dynamic programming method can be used to solve resource allocation problems efficiently when assumption 3 is valid and when the amount of the resource allocated to each activity is a member of a finite set. So, here out of these three assumptions, even if 1 and 2 are not applicable and only 3 is applicable, then we can make use of dynamic programming method to solve the problem. General resource allocation problem. The problem of determining the allocation of resources that maximizes total benefit subject to the limited resource availability may be written as max sigma RT xt t starting from 1 to small t to capital T, and similarly st sigma t starting from 1 to t capital gt xt and which is less than equal to w, where xt must be a member of the set 0, 1, 2, 3, etc. And this is we are discussing generalized resource allocation problem. To solve this dynamic programming, define FTD to be the maximum benefit that can be obtained from activities T, and time period is as T, T plus 1, T plus 2 till we have T. If D units of the resource may be allocated to activities T, T plus 1 till T. We may generalize the recursion to this situation by writing Ft plus 1D is equal to 0 for all values of D. FTD is max RTXT plus FT plus 1 D minus GT XT, where XT must be non-negative integer satisfying GT XT less than equal to D. So, there is a turnpike theorem also available in dynamic programming problems. Turnpike results abound in the dynamic programming literature. Why are the results referred to as turnpike theorem? Think about taking an automobile trip in which our goal is to minimize the time needed to complete the trip. For a long trip, it may be advantageous to go slightly out of our way so that most of the trip will be spent on a turnpike on which we can travel at the greatest speed. Equipment replacement problem also finds a solution through use of dynamic programming technique. Many companies and customers face the problem of determining how long a machine should be utilized before it should be traded in 1-for-1. So, how long we must use an equipment, that decision is to be taken, and that is taken through dynamic programming. Problems of this type are called equipment replacement problems and can be solved by dynamic programming technique. An equipment replacement model was actually used by Phillips Petroleum to reduce costs associated with maintaining the company's stock of trucks. So, equipment replacement problem also finds solution through dynamic programming techniques. Formulating dynamic programming recursions. In many dynamic programming problems, a given stage simply consists of all the possible stages that the system can occupy at that stage. So, viewers, we have discussed so far the meaning of dynamic programming. What is the difference between linear programming and other techniques as compared to dynamic programming? In nutshell, we have discussed that a problem can be broken down into different stages, and these stages can be added sequentially, and we know that each stage we can find its solution, and we start from the end point till we reach the starting point, and at each stage we find the best possible solution. So, we get the solution for different stages, we add them together, and finally we get a solution to the problem. We have also seen that dynamic programming finds its place in different problem areas, and we can find a solution to these problems. And with this remark, I am now ending my lecture. I hope the viewers have understood the concept of dynamic programming. In future, we may discuss mathematically further how the problems are solved.
With this note, thank you, sir. Thank you so very much for giving us such a productive session. And I would like to tell you all that you can access lectures, that the lectures of CEC, or if you want to access this particular lecture, you can access through YouTube, on which we daily upload our lectures. Thank you, sir. Thank you so very much.